Hi, I'm Anurag, co-founder of Avail, presenting one more episode of Avail's Whiteboard Series. Today we have Carsten from Cartesi with us, and we are going to do a detailed walkthrough of Cartesi from him. Welcome, Carsten.
Thank you.
Carsten, if you could start out with a very brief introduction of yourself, and then we can go from there.
Yeah, so I actually started out as a community member in Cartesi, playing around with the technology. Like, I'm not a co-founder or anything like that of the project. I saw the Cartesi machine, and I saw at that point computational oracle, and I started playing with it, and I was amazed that I could basically develop things for blockchain where I could treat it just like another computer, right? Like a computer that's capable of running anything from, let's say, Node.js to Rust, or even stranger things like PHP or something like that, right? And it was very appealing because it was a huge leap from kind of like the usual frustration that you have with blockchain development, essentially. In July this year, I joined as a board director in the Cartesi Foundation, where my company is a grantee of as well. And we play around with what you can do together with Cartesi, sequencers, data availability, and kind of like seeing how the future of verifiable computing looks like together with these amazing new technologies.
Sounds awesome. So maybe what we can really do today is maybe I'll just set out the rough agenda. Right? Like maybe we'll initially go through the high level of the Cartesi framework.
Yeah.
Then we'll maybe go a little bit into the motivations. You already mentioned some of this, but like how is it this qualitatively different from a developer experience? You know, like maybe we'll get into that. Then of course we'll go through in detail on the architecture. Then maybe we will talk a little bit about how verification happens on a contract on Ethereum in the case of the current implementation rollups. Maybe we also spend time on how like an optimistic sovereign rollup, like a P2P verification game can happen. So things like that. Let's see where it goes. So maybe if you can start with a very high level introduction of Cartesi.
Yeah, so one of the first things you need to understand about Cartesi is that it's not like meant to be, let's say, a general purpose rollup, like let's say something like Arbitrum or Obstack or similar kind of thing is. We are very focused on app chains because that's where we kind of believe that this is the best way to scale, especially with things like shared sequencing and so on coming up. And right now we have the Cartesi Rollups framework, which is meant to kind of like settle on top of an Ethereum layer 1 and using the Ethereum layer 1 or layer 2 as the data availability layer in this particular case, right? And the premise is really like basically simple. Like you shouldn't need to have the giant leap that people normally need to have in order to completely understand how the blockchain works, completely understand how the EVM works, how Solidity works, all the pitfalls and so on. But instead, the people that don't actually know anything about how you make verified computing can then jump into it. For example, in one of our hackathons, I think it was in Lisbon, there was a robotics engineer who didn't know anything about Solidity, didn't know anything about how Cartesi specifically worked. And she took a large language model and put it inside a Cartesi rollup, and actually was able to do interference as in getting queries answered by it in this particular case. So it really shows the kind of like the potential of the design space here. And Cartesi is not a new project. It's not that well known because it's kind of like something where it's been taking kind of a while to kind of like get completely general purpose, but well, we have been around since like 2018, something like under development. So it's not like we are making some kind of like new virtual machine. It needs to be tested, be battle tested. What's special about Cartesi is that it doesn't try to make a custom virtual machine. It implements what's called RISC-V. It's an open source instruction set. It's royalty free. You don't need to pay a particular entity anything when you're actually using it. It's all open source. The test cases are open source. The specifications are open source. So when we've been developing this, we can actually really quickly check that this virtual machine is acting just like, let's say, a normal RISC-V actual, let's say, chip would be working. So it makes it quite useful because then something like Linux will boot up on it, and you can basically use the existing kind of like compilers and so on that you already have for that. And this, we personally think, is quite a fresh breath in the blockchain space because I think by now, after 5 years, we have to realize that making custom virtual machines, having custom tools, custom languages ends up in more damage and confusion and developer frustration than is actually needed.
Yeah. Okay. Makes sense. So I think so. What we've now understood is like Cartesi is like a like application, like focusing on application specific chains with the RISC-V architecture, so that like developers don't really need to reinvent their tooling, for example, and so on, right? Like, but like, can you take us through, let's say, how, let's say, verification works, for example, or like
Yeah. So one of the properties of the Cartesi virtual machine, because normally when you're talking about, let's say, emulator, for example, let's say I'm playing, let's say, a Game Boy emulator on my, that shows my age, talking about Game Boys instead of like Nintendo 64 or something older, but you know, that it's completely deterministic, right? So yes, you can run it in a kind of like interactive mode where you can like typing and then getting responses and so on. So it's like just emulating some chip or something like that.
Yeah.
But the Cartesian machine is completely deterministic. So normally we talk about that there's always kind of like some kind of agreed starting point, right? And then you run a bunch of computation cycles, and you always end up in the same point every single time, right? So if I give you a particular Cartesian virtual machine image, you're able to run it in exactly the same way and end up in the same result, right?
yeah.
And okay, so let's say that I'm trying to prove to you a computation is correct, right? Yeah, we'll get let down a little bit in how kind of like optimistic rollups work in this particular case. This is kind of like the same way that something like Arbitrum and optimism also work, right? But they have an optimistic, where Arbitrum has like the WebAssembly kind of virtual machine, and Optimism is kind of like using a MIPS-based virtual machine where they just compile a single program to it. What we're doing is taking kind of like a general purpose machine in general. So, okay, so I'm trying to prove to you, or let's say to a blockchain, that my virtual machine ran from this point to this point and it held it here, right?
Yeah.
And I'm running the computation myself and say, hey, that's not the hash that I got, because the Cartesian machine, it's like, if you imagine a little bit like a RAM, right? A piece of RAM like this, memory, the state, that's maybe the kernel or something like that. My handwriting's terrible. But essentially what the hash represents is a Merkle tree of every single word or 8 bytes inside the machine, right? So basically, for every single piece of the memory of the machine, you can always go and prove that what is the state at a particular point. So you basically make a Merkle tree, you get the Merkle root, and that's basically the state of the machine, right? Okay, so now we are in a dispute. We don't agree on it, right? So what we can then kind of like do is do what's called, let's say, a bisection. Basically, find out where did we agree and when did we stop agreeing? Because this is like in time, this is linear, right? And you kind of like do it in kind of like what's called a binary search. You kind of like start with half, and I say, okay, do we agree at this point? Yes or no? If we agree at this point, then I need to go to the next half. If we disagree, then go here, and eventually kind of like narrows down in less than log 2 of the maximum amount of cycles to a particular point where we at least either agree about something, which could even be the start of things, and the next step we're after, right? And this is where the blockchain comes in, right? Because it's supposed to act as a judge here, because there's no impartial judge that you can otherwise make here, right? So we go in and make what's called a step, because the blockchain is powerful enough to run as a single CPU cycle, right? It doesn't need to run the entire computation, but it does need to run a single CPU cycle. So we go in and say, I'm trying to prove that this state plus 1 cycle equals this state, right? And this is a hash, and this is a hash, right? So how do we do it? I kind of go in and do this. So basically what happens then is that when something like RISC-V is executing, essentially what is happening is that you're always reading a bunch of stuff from memory, like for example registers, or you're reading stuff from memory, and then you do some execution, and then you write back out into the registers and the memory. And because all the state of the machine is memory, then we just basically, it's like proving that we could do these reads inside the original hash where we all agreed. We check that the values match when we prove them. So we kind of like do a Merkle proof verification in this particular case. And then we execute the step, which basically says, okay, I want to read from this cell, this register, and I want to write out to this register. And I basically update the Merkle tree using by providing the kind of like the siblings of the Merkle tree in this particular case. And the blockchain will then independently arrive at what it believes the hash is. And it can then judge if this particular claim is true or not, right? And this is kind of like how this is optimistically provable. We have also in Cartesi done experiments with, let's say, proving the full execution of a Linux machine in zero knowledge as well. So we can also take just one step in zero knowledge if that's actually what we wanted as well, but it's kind of like more in the future. Because the virtual machine can kind of like start and stop, then you can also do patterns like, let's say, and this is how our rollups are kind of working, that let's say we start up the machine, we boot up Linux, and then at some point, basically, we start waiting for the next transaction, right? So we don't need to kind of like boot up Linux every single time that we need to kind of like process a new transaction. And we then get woken up again when there's a new transaction coming in, and we do our processing, and we halt again, right? And we take a new transaction in, and we halt again. But you can also do it in like things like, let's say, something like AWS Lambda, right? So it does the same thing, like snapshots, runs up to the point where it's kind of like waiting for a transaction. It does something, but it also stores a state elsewhere. So it's more like a Lambda kind of like approach where you kind of like accumulate information out, right? So this is kind of like the basic building blocks of something like this machine works, and it basically allows us to prove the execution of a Cartesi machine to a blockchain or somebody else, and you can kind of like always make proofs about what the current state of memory at a particular location is. So for example, when we get a transaction in, then we can go and say that, well, this memory area is where we got to get the input of the transaction, and then we kind of write the output again out, like for example, what the blockchain needs to know about the state.
Okay, makes sense. So we have some idea of like how the verification process in the Cartesi machine works. I just want to understand a little bit about, like, when we are talking about, like, let's say application specific machines, right? Like, I mean, what does the storage structure in that sense look like? Why are you calling this a application specific, like chain specific movement? Like, do you have like a standard storage structure for the blockchain? Are people able to customize? Like, how does that work?
So this is a little bit like, let's say, something like Dfinity. If they're doing the Rust and canisters, right? So basically, you have everything that's in your memory. So okay, let's look for a moment how a Cartesi machine looks like typically, right? So a Cartesi machine is like an address space, but inside here it can also have drives. Like for example, this is the application or the file system, right? And it can also have like, let's say, a drive where you get, for example, the input in, or you can write the output to, and so on. So you get basically the entire Linux file system you can write to as well. You can put things in memory if you want to access things directly, but you can basically, if you want to write something with SQLite, a database, and host inside a Cartesi machine, it will basically just work.
So I just want to clarify. So the storage I'm talking about is primarily, so in the case of, let's say, the EVM, right? Like, I mean, so you have this generalized or shared
Merkle
state, Merkle tree, right? Like, I mean, and that is shared across applications. And so I'm just trying to understand, when you are framing this in an application chain perspective, are there changes that make this application like chain state specific? Like, what are those changes like?
Yeah, so in this model that we're running with currently, basically what you're doing is changing the machine state, right? So you can also argue to some extent that, let's say, there's no such thing as the external storage of the EVM, because like it's always existing inside a particular memory space, but essentially the entire state exists inside the memory of the application, right? And because the Cartesi machine is a 64-bit machine, essentially we can store much more data than we can in a way, right? But at the same time, we just need to store kind of like the latest snapshot at any point.
Okay, makes sense. So let's go through the typical life cycle of application rollup on. Let's start with Ethereum, right? Like, that's where most rollups
let's start with Ethereum. I'm just gonna erase this for a moment. Okay. That should do.
Yeah, that
Okay,
should
so
do.
the typical, like, on Ethereum layer 1, like, as you know, the way that people are typically using the Ethereum one is essentially you're using the Ethereum layer 1 as a sequencer, right? Like, you're posting, let's say, in our particular case, we call it an input box. So typically there's some kind of smart contract that basically describes that when I have deployed this, this is where my application rollup comes in, right? So we have a bunch of kind of like inputs, which are basically transactions, right? Or multiple transactions, or bundles of transactions, and so on. So this is kind of like how it looks like from point of view of rollup, because like as might have been explained some other places as well, like the state of a rollup is kind of like determined by running a particular function over some previous state, with the transaction in this particular case yielding a new state, right? So basically, at any point when it has been committed to the Ethereum blockchain, essentially at that point, anybody can go in and kind of replay it if they have the same kind of like function or the state available to kind of like find out what's the latest state, right? So that's the bare minimum for, let's say, a rollup on Ethereum, right? But there's also sort of kind of like, let's say, gotchas in dealing with Ethereum. There's stuff like censorship that needs to be taken care of, like I guess in that, let's say somebody might block your ability to send a transaction. There's things like that there might be reorganizations of the chain happening. So until kind of like that let's say the transactions have committed completely to the Ethereum chain, technically speaking, it's not like completely settled. And it can be a little bit of a pain when it comes to kind of like arguing about like what's the latest state of a rollup.
Yeah, makes sense.
Now, what we then have is in the current rollups framework, which of course we have some services that you need to run somewhere. This is not the most practical, but that basically goes in and kind of like reads these and kind of like provides the APIs for people to read the state of these machines at this particular point, because they can go and reach into memory, check what the state is at a particular point, and kind of like be a part of kind of like making people understand the rollup. But there's no reason why, let's say, that you couldn't, let's say, run a app chain node in something like a browser. It goes and reads Ethereum, pulls in transaction to update the state and so on. But because, for example, the Cartesi machine is running in everything from WASM to MS-DOS, so it's quite powerful in that regard. Now, the funny things. So at this point, like the ordering and the kind of like the sequence is kind of like protected by Ethereum security, right? But the challenge comes in, and also on top of this, the rollup also knows what the latest state of Ethereum is, right? So there's some kind of like block hash. So, for example, let's say that now I want to send a message from Ethereum layer 1. So now we're getting into a little more like bridging, right? We are getting into that, for example, a smart contract on Ethereum want to send a message into my rollup, right? So you can go in and say that I can make a special transaction or something like that, basically making a Merkle proof that something existed in a previous Ethereum block, and here's kind of like the Merkle proof that this data is actually truthful, right? So this is kind of like the way that, for example, you can signal that, for example, let's say if I want to send a token in or some F or something like that, and make it kind of like be owned by that rollup and kind of controlled by it. So this is kind of like the one-way bridging. Like one-way bridging, L1 to L2, that's easy. Right? L2 to L1 is not. So there are kind of like two different approaches because it's a little bit like I have a little bit like two different virtual machines, and I need to prove one thing from one virtual machine to another.
Correct.
And this is where optimistic proving comes in, where I was talking about before. Because then it comes down to that I want to have this state. I want to have that calculated in some way, or at least a part of the state that relates to kind of like what messages does this machine want to send to the outside. So it doesn't mean that they necessarily need to, let's say, go in and, let's say, process every single little transaction. It just needs to process the ones that are kind of like relevant to bridging out, essentially, like sending a message out. Because, but anyway. So we want to do this, right? So let's say that now I go in and, okay, that's the optimistic approach and the ZK approach. I will talk to the ZK approach in a moment, right? So I go and claim that. I say that, let's say that this state, and this one is agreed upon at this point, state 1 and state 2, right? And I go and say that this, after running it to completion, ends up in this new state. And that's the claim I put out, right? And then basically you have to kind of like wait for a challenge period, it's called, and you go out and wait. At the moment, people call it 7 days. There's a lot of discussion about what these 7 days mean, but the one I'm sticking to is that it takes 7 days to organize a social fork of the Ethereum blockchain, or which basically seems to be the same period of time it took when the Shanghai Dev Connect, I don't know. Anyway, when that happened, and basically having to kind of like go in and make an emergency patch to the network, right? Some argue about that this is not a fair pressure to put on, let's say, the validators and so on. There's probably better ways to do it, but waiting for 7 days seems pretty okay because people might potentially censor it, right? Okay, so then basically we have 7 days, right? And anybody can go and say that, hey, I don't believe that your state is correct, right? But if nobody goes in, or everybody agrees, in this particular case, and that there's a lot of definition about what does everybody mean as well, you can then go in and basically settle straight ahead to the blockchain if, let's say, there's no disagreement about that this is correct. So it's less than 7 days. In most cases, it's going to be that, because when you're going in and making your claim, you typically need to put down, for example, the deposit or some kind of insurance that indeed that you're not doing things badly. So in case that you can't just go out and say that, hey, this is wrong, this is wrong, this is wrong, and waste a lot of computing power to do it. But in case that you do disagree, then that's where, for example, let's say this bisection game comes in, and you have between, let's say, the prove and the verify, this kind of like game to find out who's right, right? And this is a thing that can, like, technically speaking, it should last up to 7 days, but there's a lot of kind of like challenging the different algorithms that you do to it. But at the end of the day, what comes down to in terms of bridging is you end up with that, indeed, that what I said was the state is correct, right? And at that point, you can kind of like execute the messages on the underlying blockchain. The bridging messages, for example, release this amount of F to let's say a particular smart contract or end user wallet and so on, or communicate otherwise. But this is just between, let's say, this is kind of like L2 to L1, right? But for example, it is also possible to have multiple layer ones, right? So it might actually be that something like L2 could actually send a small message to a layer one, because he actually wants to send something layer 2 to layer 2. So you actually go in a much faster proof to another layer 2, because the problem with layer 1 is that computation is very expensive, but on other layer 2s, computation is very cheap. So for example, you can actually make them even process parts of kind of like your particular messages that are coming out. So right now there's a lot of kind of like, oh, but I need to move my F out from Arbitrum into for example, to Ethereum, but like in practice, there's things like, for example, Hop protocol and similar other kind of like setups where you can actually do this much cheaper because it's like kind of like liquidity essentially flushing around. So the other approach that also some people do is basically they go and say this computation, and they then make it with a set gate proof as the zero knowledge proof instead, where basically you're proving in a very small computation time that this actual process or this machine changed from this state to this state and provides this very small proof, like 200 bytes or 400 bytes or something. There's stocks which are bigger, which is 200 kilobytes, and snarks that are smaller, but recent advances in things like RISC-0 with recursion and stock to snark basically means that nowadays we really don't need to write anything specifically for the EVM because it's just so practical. Just write it up in Rust and get it run with these technologies. So that's kind of like the framework, kind of like how we communicate between these different layers, right? But as we also were talking about, this cold data, getting things because this data is permanently on the Ethereum blockchain, right? Like you can always access it. Like, of course, you need to have access to the archival nodes and to kind of getting all the old transactions in, because it doesn't get stored in the state. It just gets kind of committed to the state where a particular hash is. And that's basically, and then also comes on top of the problem that something like Ethereum is very restricted in the amount of data you can actually push through. It's very expensive, and it's not very good for user experience because also it takes you at least 12 seconds of block count plus a number of confirmations to actually feel that this is actually settled. Which is why people are looking at things like state availability and sequencers, which I think we can then kind of like jump to a little bit. Maybe you want to talk a little bit about data availability, since this is also your territory.
Yeah, we'll get into that. But before that, I just wanted to just complete this cycle in general. So if you want to run the Cartesi machine as a Ethereum specific rollup, right? Like so one is that like typically either you do send transactions directly to Ethereum or via sequencer. We'll gloss over that at the moment. But you have the, let's say, the finalized state here, right? Like, and then there's a Cartesi machine here which you are sending. Users can send transactions to.
Yes.
Right. Like, and so the idea is that users, developers will be able to build applications in, let's say, any language supported by RISC-V, Rust, for example, and such. Right. Like, and then users send. So let's go through the entire user flow as well for a specific
the user flow for the developer flow or the user flow
for the user, let's say.
Okay, but for the user, like it's a little bit like how you would, let's say, because the user usually comes in through a front end, right? So it usually comes in the front end. They have a nice browser, URL bar. Do people still use URL bars? Anyway, and they basically typically connecting this particular case to some kind of like blockchain node, like most people are connected to Infura or Alchemy or something like that. But in this particular case, it's like Cartesi node.
Cartesi node,
right? And that Cartesi node is the one that kind of keeps up to date with kind of like what's the latest state of the blockchain.
Yeah.
This you can of course argue with the same kind of like problems with, let's say, with Infura that this is not insecure because you're trusting a third party in this particular case. But there's no reason why, when you're making queries to the Cartesi node, that you can't get a proof out that this actually corresponds to the machine state, and you kind of like slash the node in one way or the other. This is just something we're not doing at the moment, but there's no reason why you couldn't, right? Or even providing some kind of set key proof that this information is correct, right? So typically in Web3 applications, these people also have access to an Ethereum node, and you can kind of like send directly these transactions to the Ethereum. Like, so basically I send a transaction, it gets merged into a block, right? And it becomes one of these up here. But you can also send to a Cartesi node that, for example, more like a sequence in this particular case, kind of bundles all the transactions together to kind of like
send it
to basically make it cheaper to kind of like send to blockchain, and also use a little bit of, let's say, optimization of economics and so on. So there's always kind of like some kind of cost that kind of like gets passed through, but like, for example, there's tricks like using compression to like reduce the amount of stuff that kind of comes in. So from point of view of the user, like it doesn't really like look that different to some extent from the application point of view. You are working with structures and outputs from your application. You are accessing the state of the application, the state of the chain, and kind of like querying it. Like, for example, we have a GraphQL API you can kind of use, and so it's just like using a normal blockchain application. So there's of course always the discussion about decentralized front ends and so on, but that's an entire box in itself.
No, so just to complete that picture, right? Like, so user sends a transaction through a front end to the Cartesi node. The Cartesi node, assuming it's in sequencer mode, periodically batches, let's say, the transactional data, puts it on, let's say, call data for now on Ethereum, and then basically from a bridging perspective, right? Like, let's say someone wants to bring funds from Ethereum to Cartesi, like they'll do like probably a deposit, like instruction to a contract, send a message. And so you'll, I think, lock the funds here, mint it here. Like, now, what happens on the way out, right?
This is of course kind of like managed by, let's say, the application itself, which is basically like, it could be anything from a Python script to something more complicated, right? And basically it makes a message out that please, you can release this out again from there. So there's no independent kind of like account layer in this particular case. It's the application that decides.
Okay. So so I'm just trying to like visualize, like because my understanding is coming from a very, let's say, EVM centric point of view, and so like there's some data structure, let's say an exit tree, for example, that I'll maintain in terms of the withdrawing.
So typically what gets out in every single state is that there's kind of like sitting what we call an output, of course. Like basically, there's like a Merkle tree essentially.
Yeah.
And you get when you're making a voucher, you can then read from the state that indeed this exit then corresponds to this particular leaf, and you can only use this leaf once when you come out. So basically, it's like a tree, right? Of kind of like outputs essentially you're allowed to make.
Oh yeah.
And then on chain, then we need to then again kind of like go out and execute these vouchers because like the state just gets updated, right? But it doesn't anybody can go and then cause these vouchers to be updated.
Okay. So basically, I mean, if I'm not wrong, it's a similar kind of mechanic where there's like let's say like an exit tree mechanic here, which keeps on syncing depending upon what messages that you send. Now let's go from a developer or from a system design perspective, right? Like how is the state of the machine, of the Cartesi machine, for let's say for a particular bridging, like so I'm talking about more about the bridging, because you really have to prove the state of this machine there when you really want to, like, let's say claim the voucher, for example. So what is really happening here when someone wants to withdraw, right? Like, what is the verification mechanism like you mentioned, of course, about the bisection mechanism, but like just a little bit detail into the specifics of this.
So let me just try to remember how exactly it's done. So, okay, we've gotten to like bypassing the bisection in this particular case, right? Like we agree on what the state should be, right? So that's kind of like a record about, like records stored in the underlying blockchain. What was the different states at different points, right? Or a commitment or some kind of like way they kind of like to go all the way back in the states, right? So from a completely technical point of view, like typically what is on the chain is, for example, let's say let's say a bridging contract, right? So for example, I have a bunch of, essentially it's a little bit like a ledger, right? But at that point, the ledger, each of these elements is like somebody made an input into the ledger, like put some deposit into it, and this ledger is now under the control of the application, right? So by the time that somebody comes out, they need to have a statement from the application in this particular case that they can then move it out. So they basically go in and say that in this state, which is it's a little bit like with Bitcoin, the UTXOs and unspent outputs essentially, right? You go in and say that in this state, in this leaf of the Merkle tree, I had this amount of deposit because like deposit, and it's supposed to go to this Ethereum address. So it's not like that I can go in and like steal somebody's output, right? It has to go to a particular Ethereum address. And that's kind of like this leaf, because this is unique hash of this deposit, of this time, of this particular state, is like a nonce, right? So you basically seal it the moment it's executed, right? So I go in as a kind of like as a bridging client, I then need to go in and execute that voucher. But it's just a Merkle proof. It doesn't cost a lot of gas, but it does cost a little bit to kind of like get the value out again. And that's basically it, right? Now basically, like inside the application, this output is marked as spent, as in that it doesn't exist in the ledger anymore, so you can't spend it anymore or bridge it out. And it's also marked on the underlying layer that indeed this money can leave. Of course, this is like a huge honeypot as well, because like this technology really just has to be very precise and straight, because otherwise somebody's going to empty the piggy bank.
Okay. So essentially, what I understand is that, like, so this structure is maintained on a contract, on the bridge contract here, and like with a series of off-chain step-by-step. So I'm still trying to get my mental model on this process here, right? Like, I mean, how are you exactly proving like this particular, let's say a withdrawal, for example, let's say here on a Solidity smart contract,
like completely on a technical level. So let's start with how it looks like from inside the machine.
Okay.
We assume we can read the state of the machine here, right? So the moment that we have kind of like want to make an output, right? We're kind of like making an API call inside the machine here. We're saying, I currently hold this amount of value. Well, at least I believe I hold this amount of value. I want to create a voucher, right? So we can have multiple vouchers coming out. For example, let's say if I want to do a disbursement of value on a payroll, for example, right? So I get the Merkle tree, right? So the state includes the Merkle tree, right? And once we have cleared the the state. I mean, this includes a list of allowable outputs at that particular point.
Cool.
And because the machine isn't is running as it's specified, like let's say if it was lying and trying to push out more money than it should, then of course there's some issues there and so on. But we assume in this particular case the application is well behaved. So once we have cleared like the underlying blockchains as Ethereum's opinion about what the state is, we basically provide a Merkle proof, which is like a bunch of, let's say, that in this particular section of the memory of the machine, which is where the voucher Merkle root is sitting, then basically we say to make a Merkle proof down from machine state to that, and then we make a Merkle proof down into the exact leaf. So it's basically like a long Merkle proof that we're basically doing, to kind of like manifest that we can do this deposit out.
Okay. So, so from a mental model perspective, right? Like, so from an application developer or a system designer perspective, right? Like how does this, like this. So yeah, I'm assuming this withdrawal or ACE messaging is.
It's initiated. It's in this particular case, the withdrawal on layer 1 is initiated by the client.
Yeah.
So there's no kind of like, but of course, everybody else can also execute the voucher, but it's kind of like just you're paying for the gas of it. So for example, let's say that it might be that I'm providing some kind of service that in exchange for some value inside the app itself, I will then bridge that out to you so you don't need to pay for the gas. Or I can do it as part of a batch of transaction, kind of like lower the cost of doing so.
Okay, makes sense. So let's go with this for now. In general, I'm assuming you have like like a set of watchtowers who will kind of observe during the 7-day challenge period, for example.
The correct states are being pushed. It's like it's not watchtowers, right? We call them Cartesi nodes. They are keeping the state and they basically participate. We are working towards that something where it gets kind of more permissionless, but essentially like they're watching and they're stepping in if there's something. I'll get to kind of like how
makes sense, right?
The permissionless thing. But I just want to talk about this from the development point of view for a moment, because essentially what you're doing when you're a developer, I'm just going to erase this because I think we're done with this topic at the moment. What you're doing as a developer is that you're essentially designing like a machine, right? So the way that you kind of like should think about it is, yes, you're designing a memory space, but kind of like the disk drives are kind of mapped into memory because all the machine state is in memory. There's no such thing as kind of like the external device, right? And so when I'm making a machine, I mean, I need a few pieces, right? Like a little bit like a machine disk drive, it needs a bootloader, right?
Yeah.
It needs a Linux kernel, it needs a root file system, right? So that's kind of like how we construct the machine, and that's kind of like command line tools to do this. So typically we go with kind of like templates. So we have, for example, let's say, I think it's BBL at the moment in RISC-V. We have the Linux kernel, and then we have a root file system, right? So root file system can basically be and this can basically be Ubuntu, right? So Ubuntu exists for ported to RISC-V, and we have done it in such a way that Ubuntu is completely reproducible. So basically, when you get the same files from the Ubuntu repositories, you end up with the exact same root file system down to the bit.
Okay.
And we can do this in a deterministic way, which is quite nice because then you can actually trust what you're running. But on top of that, you also need to kind of have something like application, right? Like just kind of like what's actually running, because like booting up Ubuntu on its own is kind of like boring because it doesn't interact with the blockchain. So the application in this particular case, like it could be different many models. I'm personally going towards that this is basically a RISC-V Docker container. This is kind of like what I'm personally working on myself. But it can be basically anything. It can be Python script, it can be anything. And as you're then basically what you end up with, when you kind of like pack things together, then you end up with a Merkle hash, right? So if you need to validate the machine, of course you need to have a copy of the machine. We are not like at that particular point in time uploading the entire machine because it might be several megabytes. We're not uploading it. We're just assuming if you're interacting with it, you at least you are expecting that you have it available. Like you should never trust an application rollup where you can't download the machine for it. It's a little bit like if you can't download the client for a blockchain or closed source, then probably it's not trustable. And then basically, well, we have the root hash, right? So now we have our main machine here, and that's kind of like starting out in the first point, it boots up and it waits for the first transaction. And that's the starting point of our application, and then basically everything kind of falls from that. But what's really nice here is that you can use all the existing tools that you know. Like for example, I can build something in Docker. I basically can start testing it locally because I can also emulate RISC-V or using Docker and communicate with the local server. Inside the machine when it's running, then we basically have, of course, we have the Linux and root file system and all the systemd or whatever else is running, right? We also have what we call the Rollup HTTP server. So it's kind of like a little bit like a helper. So if you're comparing to something like, let's say, an AWS cloud server, for example, like a VPS, right? Typically, there's some kind of HTTP server you can get to kind of like get metadata and kind of communicate with to kind of like interact with the underlying AWS environment. So it's basically the same thing, right? So when my application starts up as part of the starting up process, then basically it goes in and then sends, let's say, that it sends basically that it's finished, right? That it says that now I'm ready, I'm booted up, and it waits for a transaction. At that point, we just snapshot the machine essentially, right? And then basically that's the interface. And then when I finished, I get back a transaction, right? And then I can send basically stuff like vouchers, notices like which like signals to the underlying blockchain.
Okay.
And I can basically accept or deny a transaction, right? Accept, what is it, the other one called reject. So basically kind of like a nice little API from the application point of view that makes it's super easy to kind of like just make a simple script because it's basically HTTP calls from point of view of the application here. So that's the application experience, right? Like basically something that's super, super simple that uses standard things, JSON, you get your payload in, you just basically manage and take your kind of your logic from there. It's not that terribly different from, let's say something like how AWS Lambda or something like a Cloudflare worker is working. Basically, they get some information in, they process it, they update the state of their object and basically go from there. So it's a nice working application model. Okay, so we have a file system here at this point, like it could be anything, right? When we actually boot up the virtual machine at this particular point, basically what happens is that we have a kind of like a roll-up HTTP server inside, a little bit like how we have in AWS. You have a particular server, you can get information about the surrounding environment, communicate with it, maybe ask to be shut down or restarted or something like that. There's a bit like an extra tiny bit that's special to the environment that your code is running in. But inside the script, it's basically the same thing like that you can send things like vouchers like we were talking about before. You can send notices, you can accept or reject a transaction to kind of like signal if a transaction is correct or not. Of course, since at this particular point the machine is essentially a big memory space, in this particular case it's like a very big 64-bit memory space, then for example, let's say if a transaction fails, you also need to make sure to roll back the state yourself. But at the same time, since you can use tools like SQLite or other kind of like databases, if you know to put an Oracle database inside this thing, this will actually work. I don't know if Oracle works for RISC-V, but you know. Then basically you can just use the kind of standard techniques you would use on, let's say, a cloud computer somewhere to revert back the state. Instead of kind of concentrate about kind of like reverting back a Merkle tree, anything like that.
Yeah.
So this is kind of like how the application developer experience works, because it's like basically just like develop an application in Docker. You don't really need to take any kind of like special understanding otherwise than, let's say, knowing what environment you're sitting inside, right?
Yeah.
So this is what I think personally that makes Cartesi amazing, because I can just start writing out an application chain just like it was essentially on a different computing medium with the security of an Ethereum blockchain, provided there's one honest validator in this particular case.
Yeah. No, makes sense. So maybe we'll move to at Avail we actually kind of released this sovereign optimistic rollup construction for the EVM, and so what do I mean by the sovereign optimistic rollup solution is that, unlike in a typical Ethereum rollup implementation where a smart contract is the adjudicator of so here you have the nodes, for example, like let's assume that you have, let's say, the sovereign nodes here, and then they basically kind of optimistically of course execute, and if they're in the case of, let's say, interactively verifying, like for example, these are like incentivized at this layer to watch the chain, re-execute the transactions and chain, and then you can construct a fraud-proof mechanism at this layer as well. And so this is our example of like just a prototype of what we wanted to build. So we built it with the EVM. So right now these run on what we call validator nodes, but typically what Avail also has is these very lightweight P2P DLI clients, which essentially do things called random sampling for data sampling. But these can be overloaded, or we can add modules for like let's say ZK proof verification, but also agents that can run this verification game in a more permissionless setting. And this is also like how we have defined this is a more permissionless setting where you can stake a native token, and then that's why you incentivize to do this. We don't have this working at the moment, but it should be very easy to.
So a little bit like, let's say, you're not just doing data availability sampling, but you're also, let's say, participating as part of the
execution verification,
the execution of the rollups.
Yeah.
Makes sense.
So in this context, right, like if of course I'm putting you on the spot, but like in general, like if we were to make this construction work with Cartesi, so like I'll replace these with the Cartesi nodes. Let's say we have a similar staking dynamic, and so there are these incentivized participants who will re-execute those transactions, and then like basically watch the chain in general, right? Like how what is the and all of this is like off chain in a sense, right? Like we are not really right now worried about Ethereum verification costs or such, right? Like I mean, this is scalable, cheap, and all of this is off chain. So how do you think about the like what are the rough, if you can give us an idea of the rough computation like benchmarks, or like complexity, in the sense that how would this work in the case of where a fraud occurs, for example?
What, sorry?
When a fraud occurs, right? Like optimistically everything works.
Yeah.
And like these nodes are re-executing and verifying whether everything is correct or not, right? Like, but when a fraud occurs, for example, right? Like, so you run this bisection algorithm, right? Like, but in that example, you are basically you wanted to give this guarantee to users who are running either these Cartesi machines or let's say these light clients, where you can give some guarantees. I don't know what guarantees. In ZK proof verification systems, you give a sustained proof here.
Yeah.
So in this case, what might be the construction like? Again, not trying to put you on the spot. Just
just thinking at the moment. But like, okay, I mean, from point of view of Cartesi, right? Like it's all, let's say, replicated deterministic computing. So it can operate not just with a fraud proof, but it can also work in, let's say, even a proof of stake kind of system, or in a way where, let's say, that you're dealing with something where you can slash somebody, right? Because you can actually optimistically prove that you didn't tell the truth, right?
Yeah.
So our, let's say, our verification games and our fraud proofs are technically agnostic, right? Like there's no reason why it couldn't, let's say, run as part of another Cartesi machine. For example, let's say if you imagine, for example, that's a top level Cartesi machine that then takes care of actually running the fraud proofs or being fed like blocks by, like, let's say, Avail in this particular case. But in general, how we are trying to move it towards is that it's a little more like a swarm, essentially, that tries to do the verification, right? Because like one of the talks that we did here on L2D space here in Istanbul and DevConnect is about permissionless referred tournaments. And it's like, it's a shift, because what we're doing is shifting around, like moving from catching liars as in people that like specific nodes that are lying about things, to catching lies, which is a bit of a shift in thinking, right? Because once you're thinking about liars, right, then it easily becomes about that it's a little bit like a permission system to some extent. But what if basically anybody, even having a toaster at home, could be doing something like data availability sampling, plus catching fraud of computation, for example, right? So it should be permissionless, that anybody can kind of like work together with it. And the way that we're doing it is that I go out and claim, or anyone can go out and claim that indeed that, let's say, in this particular, let's keep it simple, that fx equals y, right? That's my claim. Somebody else might say it's z, right? But everybody agrees what x was and what f is, right? And basically you then start having these claims fighting against each other. But we're doing a little more than that, because basically what we're saying in terms of the computation, we're not just saying it equals y, we're also committing essentially from the starting point, which is fx in this particular point, and a bunch of kind of like the intermediate steps to make a very heavy commitment on what the, let's say the and this is hold state, on the, let's say, what are the kind of the intermediate cycles? Because what this then means is that as you're doing this bisection game, if you agree or you disagree, you're providing proof at the same time when you advance the game, where you can't lie about what the intermediate states were. And this basically means that we do away with the notion that is one player that's advanced in the game. Instead, it's a team, a little bit like a football match, right? That it's X claim Y versus claim Z, for example, right? And you can have many different ones. And kind of like then, because there's this strong commitment, then basically you end up always in this way, anybody can push a transaction in, right? That becomes more like kind of like a swarm game in this particular case. And it also works so much nicer even in things like, let's say, a data availability today, because basically what you end up having is a series of messages from anybody who can send it. There's no particular, we don't actually care about who's actually sending it. But if you've been claiming that this is this, of course there will need to be some kind of stake on it, right?
Yeah.
But every people that agree in this, what's interesting about our algorithm is that the people that agree on, compared to, let's say, all the sipples or something like that in this particular case, they are stronger together, right? Like naturally a football team of 1,000 people that are fighting together towards a particular goal is stronger than against anybody else. But the amazing thing about our particular game is that it an honest player in this particular case can't be beaten in a game.
Yeah.
So that's where it kind of like also gets interesting when in terms of like, let's say, because like this is also a little bit the problem with, let's say, optimized chains, like who's going to validate it, right?
Yeah.
And with small application chains, where you're going to find people for that.
Yeah, absolutely.
This is where something like data availability sampling, because data availability sampling on its own is not very strong margin either. In terms of kind of like incoming cost to kind of like the value and so on. But if you add something like verification and so on top, then, but this is all about incentive mechanisms.
Yeah. I mean, basically, the challenge with doing systems like that is always, in general, like, why will someone do this, or how will you stop fraudulent challenges and stuff like that, right? Like, that's always the cryptoeconomic challenge here. So I would be curious to understand, like, let's say in that particular, like where you're saying you're not catching liars, but trying to catch lies, right? Like, how does that, maybe too much to get into details, but, like, if you can just point the reader, the viewers towards, like, how can we learn more about that?
How we learn about more of this algorithm in this particular case.
Like, in the sense that, like, when you mentioned that, like, you're trying to change this to a more liars versus, like, lies.
Lies versus instead of liars.
Yeah. So how does that mechanic work, and in the sense of the cryptoeconomic sense in general? Who's incentivized, who's not incentivized, who can...
Like where you can learn more about it.
Yeah.
So
exactly.
there's a talk coming out from L2 Beats that was done here the
okay,
other days. And there's a very good presentation on that I recommend everybody see, because it actually also explains the existing models a lot better than any other site I've ever seen. So, but there's also academic paper about this topic. It's a little hard to get into, but it also exists.
Okay. Okay, makes sense. Makes sense.
Can you just do a quick high level just about like Avail, like because like my impression is that Avail is like yes, it's digital, let's say availability layer, but is it multi-rollup or kind of like how do you see it?
Yeah. Okay. So how we see it is like, so the motivation behind why we are doing Avail is essentially, like we've been seeing this rise of rollups over the last like 3 years. So this project was started within Polygon in late 2020 because we realized that data availability would be a huge concern going ahead because of this whole thing of rollups going off chain and like needing massive data availability. And so if there are a few rollups, that doesn't really matter. But like now we are seeing a world where like EVM rollup stacks are being commoditized. There are like various arbitrary execution environment rollup stacks coming, right? Like like you have Cartesi, for example, but you have things being built on Risk0, for example, like Sovereign Labs, Stacker Labs, for example, is coming with a custom runtime. I think they were talking to you guys also to incorporate the Cartesi machine there. And then like Maiden by Polygon again, and Fluent, ZK Wasm, so on and so forth, right? Like, so there's this whole explosion of rollups and rollups execution environments. And like if we imagine like 1,000, 10,000, a million kind of rollups kind of a scenario, right? Like and so really they need to depend on the base layer for like ordering, consensus and ordering of their transactions. So essentially like, so Avail is certainly like an L1 that focuses on providing like dataability at scale. But essentially it's a consensus and ordering mechanism for these rollups on top. And so we imagine with this increase, like there is no real like we want to take cost out of the equation for these rollups, right? Like rollups really don't need to think how expensive call data is, like, and so on and so forth, right? Like they should just have like this variety of.
But there's also kind of like a little bit the difference from our explanation earlier on, which is that the Ethereum blockchain technical keeps all the transaction data, right? But with a data availability sampling, you only keep the commitments to the data, right?
So basically it totally depends on the configuration. So of course we keep the commitment. So our blockchain is based on, so what we take is take in the data, erasure code it, create these KZG polynomial commitments, and then they propagate these validity proofs to the light client P2P layer, right? Like so like the data storage is a node configuration thing. So we don't initially at launch, Avail is not going to prune any data as such, so it's going to be remain.
So you're going to participate yourself as a part of the like a distributed hash table and kind of like looking up data and so on, right? Because I presume that kind of like you can always kind of request the blocks over a network to some extent, right?
So actually, see this base network, it's actually an L1 in the sense that like this can house up to 1,000 validators. It runs something called Grandpa Babe consensus. So
that's the one that
Polkadot uses. Yeah. So this can house up to 1,000 validators. In the future, after we add BLS signatures, this can go over 10K validators as well. So this is the layer that takes care of the initial ordering, erasure coding, commitment creation, and coming to consensus on the blocks.
So let's say that I'm an application chain, right? I'm running on top of your stuff. Like if I want to do archiving, right, of my application, like I kind of like need to keep a little bit of your history of the Avail chain, right? But I don't need to, let's say, make a backup of every other rollup. Right?
No. So basically, I'll just explain, right? Like, so quickly you have this KZG commitments, then you have, like proofs generated that you can generate here on a full node, but also on this light client, for example. And essentially, this is like, here is where the magic really happens of sampling. So each LC has, is part of the DST, for example. And so this is a separate P2P network with like each light client talking to each other with some fragments of the data. So the first LC will bootstrap off a full node or a validator node, but then any other LC can, like will first query another LC, light client. If the data is available here, it's fine. It populates its own DST. But then basically if not there, again go to full node again. But like after a few samples, like even with 100 or so clients, it should be able to propagate.
But like, let's say on archive thing, like let's say I'm providing an archive from my app chain, it's really easy for me to prove that it was part of the Avail chain at some point in time, right? And
so we have this concept of app client,
which is like a virtual machine ID kind of like thing.
Yeah. So we have this concept of application IDs. So you can consider this as like Rollup 1, Rollup 2, Rollup 3.
Yeah. How wide is your ID? Just out of curiosity. Like, is it 64-bit or is it like?
I can get back on that.
Yeah.
But essentially, so basically, once you have that, right, like you can run this application-specific light client, and then it just retrieves only the that specific
data interesting to you, right?
Yeah. So, and the interesting thing is this data is of course stored for a period of time. Here we don't prune at launch, no prune at launch. So this will be there for a year or more. But this data also gets replicated on the DHT while you're sampling. And this app client can also have long-term data storage.
So basically, as long as there's at least one archive existing that's publishing to the DHT, I can always go and check that this was part of a particular ordering and so on.
Yeah. And we are also working with like Filecoin like providers to
try to go on
pin it on IP.
Pin it like IPFS.
Or of course we have archival nodes.
So this is maybe a little bit of a technical question. So of course you're working with KCG commitment in this particular case, but let's say the individual, transactions, like are they KCG commitments or are they commitments to like, let's say SHA-256 hashes, or like how are you seeing it?
So basically, what we
like chunks in this particular case.
Yeah. So what we basically do is construct this M cross N matrix. So we take in data
and chunk it up,
chunk it up into rows and columns essentially.
And then add some error correcting information as well. Okay,
exactly.
So the usual way, basically, right?
Yeah. So like a 2 MB thing is a 256 into 256 matrix. So we will basically erasure code it like.
So you chunk all the data into something like, let's say 32 bytes or something like that, and then basically like make namespaces and those kind of things, right?
So this is like the 2M. So M cross, we start with the M cross N, get into like a 2M cross N structure. Then we create commitments to each row.
Yeah.
So this is like commitment 2, commitment N. And this is Cn plus 1, Cn plus 2n.
But from application point of view, I never see that. I just see basically transactions, right? And applicate like.
Yeah, you don't need to like this is.
But it's only in terms of like proving and so.
Yeah, you don't need to understand all this.
Of course, that's the entire all the dance how it looks.
It's just for application. Correct. Application chains just need to like there's a standard API that you read, and it's a very powerful API that you can read, write, for example, and all that. Essentially, like what we are also now trying to ask sequencers is to embed this application specific light client in the sequencer.
Okay.
So that.
But you also do a little bit of sequencing yourself, don't you? Or
Yeah.
Like I can trust that kind of like if that app block is in a particular order.
Yeah.
Okay.
No, so this exactly works.
So you're doing some kind of sequencing to some extent.
Yeah, absolutely. So this is basically like let's say I said we provide consensus and ordering as a service. So this role plays the exact same role that Ethereum plays when you use it for call data. Like it doesn't have an enshrined settlement layer.
Okay, so from Cartesi point of view in this particular case, like when I was talking about transaction coming to the machine, it gets written into it. Essentially, from our point of view in this particular case, we follow your chain, we get a block height.
Yeah.
We have blockchain. We have a little bit like our network interface here. We get messages into. We then run the machine, and we can catch it up from that point of view.
Yeah.
So, do you also commit your state to Ethereum? I guess you're going. Which we don't need to get into kind of like the gory details of it. But let's say if I wanted to bridge some information on my state to Ethereum, like I would naturally need also the ordering, to start the computation, right? So.
Yeah, so if you are interested in construction, like where you need like to bridge to Ethereum, like assets to be bridged from Ethereum, etc. So typically you will have a contract on Ethereum, which coordinates that, right? Like what we do, like we have a bridge from Avail to Ethereum. And so this is basically, so we use Grandpa. So we've built like a ZK Snark based Lightline bridge, so which verifies consensus of Grandpa. And see, we basically
Is this construction of the, let's say, the proof for that something I need to do as an app chain?
no, nothing.
Like, so you have, you have a little bit like a service that does that,
we have like a relayer service that, you know, like
is it permissionless or
at the moment it is not like, but I mean, like basically we intend, I mean, see, it's really, there's nothing here that is there is any trust assumptions, because essentially what we create is the prover creates.
You can't cheat, basically.
Yeah, you can't cheat, right? Like, so the prover creates this ZK Snark construction. Typically, anyone can relay it. We just haven't gotten to the tooling yet, but it will be. But there is no trust assumptions in using this relayer.
Okay, and I presume that basically like this snark then commits to some kind of like commitment.
Yeah, it commits to the data root specifically.
And then can my light client then construct the proof from there?
No, so if you are
like I'm talking about, let's say, Merkle proof from this data root.
Yeah, so on in the specific case of Ethereum, right? Like, I mean, you're wanting to provide guarantee of inclusion of your rollup transaction data on a contract, because the contract can't do any sampling in that sense. So that's why the contract just proves inclusion. That, and we provide an attestation that 2 by 3 plus of the validators have attested.
Okay, so it's like a proof of stake in this particular case.
In this particular, for the case of a Ethereum like bridge.
Okay, but I can get as far down as getting some kind of like proof relayed or calculated to Ethereum that one particular transaction exists and it's at a particular index in a particular block.
Yeah, we can do the querying. So you can basically do a Merkle inclusion proof on the data root.
Yeah. So basically, like, just continue connecting this to Cartesi. In this particular case, basically we have our machine hash.
Yeah.
We patch essentially
either
the hash of it into it and use something like a dehashing device as in a pre-image oracle, basically, and then we're basically able to fetch it then from there.
Yeah. In the case of a more Avail native rollup, like a rollup that runs totally on Avail, right? Like where you like you have this Cartesi machine writing to Avail, for example, you can, so there you don't have a 2 by 3 assumption at all. You can actually have embedded this app light client into the sequencer or the wallet, and they can trustlessly verify, because they are reading the headers of the Avail chain, and the headers has the commitments. These commitments as well, so they can actually verify it on their own. So this is a honest minority sort of assumption that you can take.
So a bit of a strange question. Do you have your light client running in a browser yet?
We have it partially, yes. We are doing some more changes for it to be used with libp2b.js, and then we will have the entire part running.
Because it's like, that's always kind of like been a little bit the dream, like that you can run something on a mobile device, like a mobile game. You know, but it can connect up, can I get the configuration?
Basically, because of our implementation is, you know, like WASM compliant, like so we compile that down to WASM.
What's your code base, by the way? Is it Rust based or
Rust based?
Okay, cool.
So I think we covered a lot of things here. Hopefully the viewers learned a little bit more about Cartesi, how Cartesi machines work in general, and you know, like how can they build application rollups using Cartesi. Like, just to end on that note, what kind of applications that are you seeing initially on Cartesi? What is the pitch that you want to make for developers to come to Cartesi?
Like my view is essentially that the reason why blockchain hasn't gotten adopted like it should have back in, let's say, 2018 is basically because it was too complicated for people to make the leap. And with Cartesi, we're seeing a very interesting shift in kind of like the audience that's actually getting into blockchain using this in terms of, let's say, the capabilities, because now this access to doing amazing blockchain-based application becomes democratized.
So great. So that makes sense. I think we can wrap that up. Thank you, Carsten, again for this enlightening session, and enjoy the weekend in Istanbul.
Thank you.
Yeah.